Hi guys. So in this video, we are going to go over the BC FRQ1 that I posted on Monday with the table of values and several different question types. So let me switch my camera over and we'll begin. That's my arm. Okay. All right. So I'm assuming we've all read and attempted at least the problem. We've got this table of values for g of x and for g prime of x. And then we also have this information here about f involving an integral of g. And we're also told they're twice differentiable, right? Which means they're also continuous. Okay, so part A, explain why there must be a number c somewhere between 0 and 9 such that g prime of c equals 1/3. Now, on the hints yesterday, I posted that this might be IVT, this might be MVT, and really that's going to depend on how this value here relates to the values I gave you up here at the table. And so kind of my rule of thumb for these is that I check IVT first, and then if IVT doesn't work, then I look for an MVT. Okay, so what does that mean? All right, so IVT is the intermediate value theorem, where you're trying to see, okay, for the G prime functions themselves, is 1/3 between any of these outputs? Okay, so 4 is greater than 1/3. Root 8 is almost 3, right? So that's greater than 1/3. Root 3, that's between 1 and 2, so that's greater than 1/3, and then 3/4 is greater than 1/3. So if any of these g prime values were less, then we could say that by the intermediate value theorem, if we have one that is less than 1/3 and one that is greater than 1/3, then because it's continuous, we would have to say, okay, therefore by the intermediate value theorem, right? Intermediate meaning something in the middle, right? So that 1/3 would be in the middle between something lesser and something greater. We could use IVT for that. However, because all of these G prime values are greater than 1/3, we can't use IVT here. So then we try to figure out how to use MVT instead. So MVT is the mean value theorem, mean like an average. And for that, we're actually going to be using the G of X row, because the average rate of change is a formula that you have been using since, I don't know, 7th grade, right? It's y2 minus y1 over x2 minus x1. If I can make that for g of x, if I can make that equal 1/3, then I can use the mean value theorem to guarantee that this has to exist. Now, you'll notice I'm saying for g of x, not for g prime of x, right? Because g prime is the instantaneous rate of change of g. So what the mean value theorem tells us is that if the average rate of change, so first of all, let me back up. It's saying that as long as your function g is continuous and differentiable, which it is, right? If it's differentiable, then it is automatically also continuous. So anyway, if g is continuous and differentiable on our interval, then by the mean value theorem, the instantaneous rate of change, g prime, has to equal the average rate of change, the slope, from one end of the interval to the other, somewhere between that interval. Now, when I say the interval, we could go all the way from 0 to 9, but we have a lot of intervals in here, right, that we could work with. We could go 0 to 3, we could go 3 to 5, we could go 5 to 9, we could go 0 to 5, we could go 3 to 9. You see what I'm saying? There's a lot of possibilities with mean value theorem, which honestly is why I would try intermediate value theorem first, because it's easier, right? For intermediate, I just need one of these g primes on that same level to be one needs to be greater and one needs to be lesser. And I didn't have that, which is why now I'm hunting for a mean value. So if I can find two ordered pairs of G that would give me an average rate of change equal to 1/3, then I'll be in business. So start with what looks simple, right? And go from there. And looking at these G values, okay, fractions, gross, the odds of a G of X being -1/20, somehow nicely and neatly giving me a 1/3, that doesn't seem like really good odds. So why don't we start with the simple stuff? If I were to do the average rate of change of these two ordered pairs right here, f of b minus f of a, okay, so the difference, right, this has gone up by 1. So my y's have gone up by 1 and my x's have gone up by 3. Do you see what I'm getting at here? That's it. That's what I want to use right here is this g of 0 and g of 3. Okay, so having determined that my route forward is going to be the mean value theorem, I'm going to write down here g of 0 is -2 and g of 3 is -1, kind of establishing those are the ordered pairs from the table that I'm using. And then kind of putting that together, f of b minus f of a over b minus a. Okay, and then I'm just going to plug in the actual values, right? So I've got -1 minus -2 over 3. Negatives cancel. That becomes positive 1/3. This is called a difference quotient because it is a quotient involving two differences. But right here, I have calculated the average rate of change from x equals 0 to x equals 3. Now, I have to write an explanation for this, right? So that for any of the like IVT, EVT, MVT, right? You need some kind of statement at the end. Now, showing this counts as like part of the explanation, right? I'm saying, okay, here's the average rate of change. But this is why we see words like differentiable in problem stems, right? That there's some kind of theorem coming in if they have to mention that explicitly. So here's what I'm going to say. Since G is continuous and differentiable, and you really could even just say differentiable, right? Because it's understood that if it's differentiable, it is also continuous. And I'm going to specifically describe the interval that I'm using, which is from 0 to 3. You don't have to say the interval. In fact, they didn't even say it up here in the problem stem. You could say the interval from 0 all the way to 9. That's fine. I'm going to just specifically mention the actual interval I am using, which is just the 0 to 3 part. Okay, so that's not a complete sentence because I'm not done. Since G is continuous and differentiable on the closed interval from 0 to 3, the MVT, and you don't have to write out the words, MVT is an understood acronym on the AP Calc exams, so that's fine. The MVT guarantees that there must exist a value C for 0 less than C less than 3. And again, I'm just saying 0 to 3 because that's actually more specific than what we were asked to do, right? We were just told somewhere between 0 and 9. We've actually narrowed it down a bit, but again, it's fine here if you say 0 to 9 because that's what they gave you to work with. So really doesn't matter. Such that, and at this point, I am just parroting their own words back to them, right? When someone asks you a question, you end up restating it as part of the answer, right? So such that G prime of C equals 1/3. And that's it. So G prime of C equals 1/3, right? I've done my explanation. I've shown Here's my average rate of change. I don't have to label it. You can say this is average rate of change. You can say whatever. And then this is the instantaneous rate of change, but you don't have to do any of that. This right here, that's full credit. Boom. Okay. So IVT versus MVT, right? IVT, you're just looking for something greater and lesser at the same level. And when I say level, I mean like this is a first derivative question. So I would look among the first derivatives for that. But since I had to go to MVT, I kind of went back a level, right? Because the average rate of change, right? We're saying that that has to equal the derivative at some point. And since this was about the derivative, we had to go back to the original. We went to G for this, right? We got this from the G row. All right. Now that was a purely A-B question. Part B is not. Evaluates the definite integral from 0 to 3 of 40x f triple prime of x dx. Ugh. Okay. I would actually come up here. This is where they're talking about f of x. And I would start working out some derivatives. Okay, so if f of x is 2 plus the integral here, and I am taking its derivative, obviously this 2 is a constant. It's gone when I take a derivative. Okay, derivative of an integral is the fundamental theorem of calculus. Dun, dun, dun. Okay, so, and I have a chain right here because of this 3x. Okay, so here's our shortcut for that part of the fundamental theorem. Here's what we do. We take the derivative of this upper bound. So first of all, let me back up. If you're doing like a derivative of an integral, right? The fundamental theorem says that if you're doing a derivative of an integral from some constant, it doesn't have to be 0. It could be 27. It doesn't matter. But if you're doing a derivative of an integral and the upper bound matches the lower bound, right? Shortcut, you can just take that x, plug it in, you're done. Because derivatives and integrals basically cancel each other out. Now, when there's a chain involved, all you have to do is take the derivative of that input function, which here would just be 3. And then you just take that 3x and you plug it in for t. That's literally it, right? It's not anything crazy complicated. It's just 3 times g of 3x. Okay. Well, B down here is asking about a triple prime, which that's just kind of extra, right? So if I take the second derivative now, this is not so bad. It's a tiny little chain, right? Derivative of the inside's 3. So 3 times 3 puts me 9 times g prime of 3x. I'm going to take a moment to point out handwriting is key right now because this is a 9 and this is a G. And I have seen some of y'all's handwriting, so just be super careful with that. 9 times G prime of 3x. And there are a few 9s and G's that are going to be coming up along the way, so please make sure your handwriting is clear for your sake and anyone reading it. F triple prime. So once again, derivative of the inside's 3, going to multiply that up here, 27 G double prime of 3x. Okay, so having done all of that aside, I can now take this f triple prime craziness and I can put that in terms of my G stuff, right? Because everything in this table, those are all G's, right? I don't want any F's. F's are weird. We just want G's. That's what we've got to work with here. So 27 G double prime of 3x. Now, I will say this. So I'm just taking that G expression with the 27 and all and just sticking it in there in place of this F triple prime. I will say that this is not the only way to work this problem. And in fact, the key that the author of this problem wrote did it a little bit differently, but this is what makes sense in my head. So I'm going to go with it. And it works. It still works. I double checked it. So, okay. Now I see a 40x thing times a derivative thing. And my cat is in the background meowing, and I hope you can't hear her anyway. Okay. See how I have this derivative here? And I have another piece. This is integration by parts. Now, when you are picking your integration by parts, the parts for your integration by parts, you're picking a U and you're picking a dV when you start. And of course, you derive the U to get a du, and you integrate the dV to get a V. So the idea is that the dV, you're picking something that's already a derivative. Ding, 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 ding. We have a second derivative here, actually. So I'm going to, first of all, I'm going to like just kind of throw that 40 and the 27 like way out at the front. Those are coefficients. We don't need those in here making our lives complicated, right? So I'm just going to put the 40 on the 27. And yeah, that's a big number. I'm not going to concern myself with it right now. So 40 times 27 times integral 0 to 3 of x times g double prime 3x dx. Okay, so back at it. This is a derivative. I want that to be my dv. So g double prime of 3x. And I'll put the dx there because, you know, that's a derivative, right? U is everything else, so u will be x. All right, du will be dx. V will be the integral of this. Okay, now it's a chain, right? So we got to think what undoes a 3, a 1/3 g prime. The whole idea of integration by parts, right, is that it's kind of helping you simplify this and literally break it apart, right? But you're saying, okay, well, I'm doing this thinking over here about this antiderivative. So kind of coming back to it now, I've got this 40 times 27 craziness. And I'm just going to do that times and some big parentheses. Okay. Integration by parts formula, super important. Yeah, it's a really, really big one. Okay, it is U times V minus integral V du. Okay, so notice the dV does not come back at all, which is kind of the point, right? That we're trying to get rid of this weird derivative thing. Okay, now the uv, this is a definite integral, right? So the uv is going to be x times 1/3 g prime of 3x. And I'm putting that in square brackets because that's already an antiderivative, right? So I'm going to have to evaluate my f of b minus f of a for that. uv minus integral v du. So 1/3 g prime 3x dx. See how that dx comes in here and like it makes sense for it to be there? That means you're on the right track. Okay. All right. Now let's clean up some stuff, right? Okay. 40 times 27 times all this business. Okay. So I'm going to start working on my f of b minus f of a for this uv part up here in the front. Now, I've got x times 1/3 g prime of 3x. Okay, so if I've got, for my f of b, when I plug into 3, I've got 3 times 1/3, that's convenient, g prime of 3 times 3, which is 9. That says g prime of 9 minus f of a is 0 because it's x times, oh, whew, nice. That's great. This whole thing just turns into g prime of 9, which, look at your table, g prime of 9 is something we can work with. Yay. Okay, scooching back. Okay, I also have this business right here in this definite integral, but it's an integral of a derivative, right? So we could just like figure that out, right? Because if this is 1/3 g prime of 3x dx, we say, okay, so if I think about undoing that chain, I would divide by 3 and I would go back to g. from 0 to 3. So that's going to be 1/9 times g. See, this might be a time to make your g's a little extra curly, of 3x evaluated from 0 to 3. Okay, now remember on an FRQ, you only have to simplify as much as needed to get to a numerical answer. This is not quite a numerical answer yet because I still have expressions in terms of g and g prime. So there's a whole lot of simplifying here that you just don't have to keep doing. But g prime of 9 is 3/4. So I can substitute that. Minus 1/9 times, okay, now I need to do an antiderivative. I need to do f of b minus f of a. So g of 9 minus g of 0. And then I can pull those from the table and then I can call it a day. So 40 times 27 times 3/4 minus 1/9 times g of 9. Quick jump to the table. G of 9 is negative 1/20 minus g of 0, which is negative 2. Okay, so right now I have my answer as 40 times 27 times 3/4 minus 1/9 times negative 1/20 plus 2. Which Mr. Passwater's key says that it is. I'm just going to type all of this because, you know, some things are worth our time. Oh, no. Some things are worth our time, guys. Arithmetic is not. And I already checked this earlier, of course, before going on camera. Haha. But that's the answer. That's a lot of arithmetic involved later, but that is it. 576. That was kind of a crazy journey on integration by parts, but like I've said, this is kind of like a super FRQ. So, you know, worst case scenario, right? If you could do that, you're ready for anything. Okay, now let's move on to part C. Using a right Riemann sum with 3 subintervals indicated in the table above, approximate the length of the curve of G from x equals 0 to x equals 9. Okay. Now, if you see right Riemann sum, that should make you think of AB until you get to the words right here, which is very much a BC question. The length of the curve of G of x. Okay. That's just a formula that you need to remember that we did earlier in the fall. But length of a curve, let's start with that. We're going from 0 to 9. And curve length, there were several different versions of it. We did rectangular first. There was a parametric version and there was a polar version as well. And obviously for the 2020 exam, we're not really concerned with the parametric and the polar versions of it. So just reacquaint yourself with the length for regular rectangular coordinates, which is the integral from a to b of root 1 plus the derivative squared. Okay, so inside this root, there's 1 plus g prime of x squared dx. Now, that g prime of x, that's what we're going to be using these right Riemann sums for. Now, when they say right Riemann sum, that is the right-hand rectangular approximation method, and that's where the table is going to be coming in. Okay, so here's what we are going to do. Switch back up here. Okay, we need g prime values from 0 to 3, and then we're going to do 3 to 5, and then we're going to do 5 to 9. So for 0 to 3, when it says right-hand rectangular, so you use the width, which is the change in x, which is here is going to be 3, right? And then here it will be 2, and then here it will be 4. And then you're going to pull the number from the right. That's all that right Riemann sum means. So coming back down here, we're going to say that our first rectangle is going to be 3 times root 1 plus, and this is where I'm pulling that g prime from the table. So that root 8, but now squared. Okay, so that 3 is coming from my delta x for the first rectangle. And then from the integral, right, I'm doing root 1 plus g prime of x squared, and that g prime of x is root 8. So we're going to have, that's my cat in the background. So my first rectangle, right, is 0 to 3. My second rectangle is 3 to 5. So my width is going to be 2. And then I'm going to use the root 3 from the right. So 2 times root 1 plus root 3 squared. And then plus 4 times root 1 plus, this one's going to be 3/4 squared. All right. So just showing that is showing the reader that I understand I'm pulling the right values and I'm multiplying by the rectangle widths. That's how you do a right-hand Riemann sum. And so really quickly, 3, this is 1 plus 8, right? So then this becomes 2 plus 1 time plus 4. 1 plus 3 is 4. Plus 4. And then, okay, now this one becomes complicated, right? Because it's 1 plus 3/4 squared, which is 9 over 16. Okay, so, and again, FRQ, this right here counts as your answer. But this is 3 times 3, so that's a 9. This is 2 times 2, so that's a 4. Here in the back, this is 4. And then getting a common denominator, right, that this is 16 over 16. So 16 plus 9 is 25. Oh, look, that's a perfect square, 25 over 16. So I've got 13 from the 9 plus 4 plus 4 times root the top and root the bottom, right? So 5 over 4. And eventually, against all odds, we got an integer answer. It's 18. So that 18 is an approximation for the length of the curve of g of x, which we know very little about, right? But we were able to approximate the length of the curve from 0 to 9 based off of what we know about its derivative, which is kind of cool, right? That's interesting. Okay, now I actually have a meeting in a few minutes. So the second video, I will talk about parts D and E. Not that it's long or time consuming, I just have a lot of meetings on the day that I'm recording this video. So watch the next one and we'll go over the next 2 parts.